So we've decided that the square is going to be our axiom, which means I assume it's true, and I'm going to use it to prove, well, on this first one here, that a rectangle is supposed to be base times height. And so here's a diagram to help us kind of sort through that thing. So in this diagram, it says that the rectangle MRVU is congruent. That's what this symbol means. It's congruent. It's the exact same size, shape, area, whatever, as the other rectangle that's in blue here, which is called SPTV. So these two things are supposed to be congruent to each other. And notice that, like any rectangle, we have a base and we have a height labeled, right? And you can see it's base times height. So we're going to try to prove that that area is base times height, but we can't assume it. Like in this idea of proof, even though we've been raised to know that the area formula for a rectangle is base times height, we have to kind of like pretend we don't know it. So we're just going to call it A. We're just going to call it A. This one's A and this one's A. And look at the other two shapes in this figure. What type of shapes are those? These are obviously squares, which is totally convenient because we know how to find the area of a square because we assumed that it was side squared. So let me show you how to make this diagram pretty easily so you can draw one in your notes, and then we will use that diagram together with a little bit of algebra to demonstrate that the area of a rectangle is base times height. Okay, so let me come back over here. So remember that we take the axiom, like here was an example of an axiom with 2 points forming exactly one line, and then we use that to help us prove more complicated things. We're going to use the area of a square, side squared, to help us specifically prove that the area of a rectangle is base times height. So here is how we would make one of these shapes. We're going to start with a very large square. And if you have a ruler or something, that would be fantastic. You can make yourself a square sort of like that. Look at this. This is perfect. It's a perfect square. Okay, and now I am going to draw myself a little rectangle up here at the top. So just use my ruler, whatever, and draw a nice straight line so that I can see that it is parallel. This one here is parallel to that one, and it makes a rectangle that's right up here. Now, whatever length this is over here, I want to duplicate it right here because look right up here. I want this square going on right here, this RNSV square. So I'm going to duplicate that length and then draw myself another line parallel to the right side of this figure here. Perfect. All right, I'm going to get rid of these lines, not by scribbling them, but by erasing them. Come on, I got an eraser here. All right, look at this. It's perfect. It's actually even better than that one. It lacks color. Well, now, but in a minute it won't. Okay, so I am going to try to prove that this area here, see now it doesn't lack any color. We're going to make this thing beautiful and red. And look at my coloring skills. Are you at this level? Probably not. Well, maybe you actually are. You might currently be in world geography where you get to color stuff like maps and rivers and stuff. Okay, so we're going to just call this thing A. Its area is A, and I know it's got a base length of B and it's got a height of H. Well, likewise, this other red one here, and you're going, what other red one? And then I'll say, hey, it's this one right here. This other beautifully colored red rectangle. It's congruent to the other one. I made it that way. I made it so that these things are perfectly the same. And it's also got a base length of B and a height of H. All right, so far. Now, let's kind of take those dimensions that we have, the B and the H, and see where else those segment lengths lie in this picture. Like, for example, this length of B is the same thing as this length. B is the same thing as this length B, right? So I'm just going to put B's everywhere. There's a B there, and there's a B there. And then likewise, this length of B right here is the same as that one, which is the same as this one down here, okay? So this one's a B, and this one is also a B, which turns this beautiful thing into a square. And by my axiom, I know that its area is supposed to be its side length squared. And since this guy has a side length of B, then its area must be simply B squared. That's easy. All right, that makes sense. All right, now let's take a look at the smaller one here and do the same kind of analysis. This length here is H, which means on the rectangle, this top one must be an H, which means that this one must also be an H. So put H's everywhere. So this is an H, this is an H. Likewise, H, H, and H. Throw some more H's in there. H and H. Hey, we have another square over there, and by our axiom, its area must be H squared. Okay? So notice that, again, at no point have I assumed that the area formula for a rectangle is base times height. I'm trying to, I have amnesia for that particular area formula, and I'm pretending like I don't know what it is. Magic is about to happen, and we're going to be able to show that that's true. Okay, now, what shape is the whole entire thing? What did we start with? What is this whole entire shape? I believe that it is also a square, and all of its side lengths are B plus H, right? We got a B plus an H. Well, what about this other side over here? Well, we also have AB plus an H. And you can say that is true for all of the side lengths. It's a square. All right, so here's the general idea of how we're going to get through this particular idea that the area of a square can help us prove that the rectangle is base times height. And it is the fact that the area of the large square here should be, that is not how you spell that word. I believe that is correct now. It should be equal to the area of all of these little pieces added together. So we have the area of the small square plus the area of this medium-sized square. That's what I'm going to call it. It's its official name, area of medium-sized square. And then these two beautifully colored red rectangles, right? And I'll just call whenever I put it together, it's just going to be A. All right, that's all I know. It's called A. So plus 2 rectangles. And the word area should probably be in there someplace. All right, so I'm running out of space. I probably need another page. I write too big, I guess. All right, so now I'm going to basically use my variables that I've put here and some algebra. Okay, so the area of the large square, its side length is B plus H, which means its area should be B plus H, all of that squared. So that would look like this. Quantity squared. That should be equal to the area of the small square, which we declared as an H squared, plus the area of the medium-sized square, which we declared as B squared, right? Plus the 2 rectangles, which we don't know what they are, so we're using A. And we have 2 of them, so it's 2A. All right, this is lovely. We have ourselves some sort of quadratic equation. Let's just kind of like expand out the left-hand side, combine some like terms, and let's just see where this takes us, shall we? All right, over here on the left-hand side, this is a perfect square. It will be a perfect square binomial, trinomial when we're done. And the way that we square this thing out is that we have 2 copies of it. We have 2 factors of it. So I just write them side by side. B plus H times B plus H. And then I'll have to FOIL that thing out. And then there is nothing to do over here on, over here on the right side. So you know what I'm going to do? I'm just going to duplicate and bring it down because I can. Okay. But over here on the left side, I need to be doing some FOILing. So B times h is a b squared. B times b is a b squared. B times h is a bh. Okay, and let's see, what else do we have? We have an h times, that should be red. Just a second, guys. Okay, we have an h times b. H times b, it's multiplication, so h times b is the same thing as b times h. I'm going to write it in that order. Make it look prettier. All right, and then one last one. H times h, we have a h squared. And then once again, because I can, I will just duplicate that, bring it down because I didn't do anything with it. However, notice that there are some like terms that I can combine up in some kind of way. So look, I've got a b squared on both sides of the equation. So what happens with those b squares? I can subtract them. I can subtract it from the left side, subtract it from the right-hand side, and they are going to cancel. All right, but not only that, I can subtract the h squareds from both sides because I got one on both sides. So, and then they will also cancel. Now, it doesn't look like anything else cancels. I don't know why that turned out to be pink. Just go with it and then combine our like terms. We've got a BH plus another BH. That means there's two of them. Do you see where this is going yet? Do you? All right. And then over here on the right-hand side, we just have 2A. And it looks like we have a common factor of 2 on both sides. I could divide both sides by 2. I'm going to divide this side by 2. Again, we're going with pink, apparently. I don't know what happened to my red crayon. And then I am left with BH is equal to A, or if you prefer, A is equal to base times height. And there you have it, ladies and gentlemen. We have proven that the area formula for a rectangle is base times height based on the assumption that the area of a square is side squared. And that's how an axiomatic system is formed. So this one, the area of a rectangle, is an example of something called a theorem. It's called a theorem because it was proven based on some simpler idea, and that one was the assumption of the area formula of a square. And you've probably heard that word before, right? Attached to the Pythagorean theorem. And the Pythagorean theorem is the same kind of thing. It has been proven lots of times based on some simpler ideas. All right, so here is another cool feature of an axiomatic system. I'm going to come back up here to the picture that I drew of these two things and get rid of the check mark for the parallelogram. All right, so now I know that the square is good because I assumed it, and I've proven a rectangle, and I have 4 more of these left, right? I have 4 more of these left. And the question is like, how am I going to prove those 4 things? And now I don't have to just base it on a square. I can base it on either a square or a rectangle. As a matter of fact, there's a special word for that concept. It's called rectify. Rectify usually means, like we refer to rectifying something as making it right, but where it gets its name is rectangle. You turn something into a rectangle. So now with my axiomatic system, if I were going to prove one of these other 4 shapes, I can either turn it into a square or I can turn it into a rectangle. So that is what the next activity is supposed to be. Using the square as an axiom, the square formula as an axiom, we were able to derive the rectangle, okay? And so what we want to be able to do is derive all of the other ones. The one that we just did for a square is the only one where you actually have to use some algebra like we did before. On the other ones, what I would like for you to try to do is take your shape and see if you can rearrange it in some kind of way. Can you rectify it? Can you turn it into a rectangle? Can you use the idea that the rectangle is base times height or the square is side squared in order to find the areas of the other shapes, which is a parallelogram, the circle, the triangle, and the trapezoid?